Well, thank you very much for that introduction. I feel like I shouldn't be speaking because it's all downhill from here. Seriously, thanks a lot for the invitation. It's a great pleasure and a great honor for me to be speaking here. On a personal note, it's been really nice being back and seeing a lot of friends. Yeah. So in these lectures, I want to talk about p-adic Hodge theory. More precisely, what I really want to do is tell you a little bit about what's called prismatic homology. It's a relatively new, well, it's like 6 years by now, Chromology theory that's been useful in understanding the mod P cohomology of algebraic varieties. And it's had a few different applications. And so the goal of this, of today's lecture is to tell you a little bit about what prismatic homology looks like and mention some applications. And then in the next 2 lectures, I'll go more into 2 specific applications, one in algebraic geometry and one in algebraic topology. And before I start, I just want to encourage people to please ask lots of questions. I'm very happy to answer them, and also to remind me to repeat the question if I forget to repeat it. OK, great. So we want to talk about p-adic Hodge theory, whatever that is. But let's begin sort of in the classical Hodge theory. A lot of the subject is inspired by what people understood classically over the complex numbers and then trying to port that over into some p-adic setting. So I'm going to begin with Hodge and Theorem. So sort of the basic theorem of Hodge theory. I guess this is from the 1930s. And let me formulate it this way. So let's say X is a compact scalar complex manifold. The most important examples, certainly for this talk, are going to be projective ones. So X could be sitting inside CPN as an analytic subset. So it's the zero locus of holomorphic functions, or equivalently, it's just the zero locus of algebraic functions. So if I give you homogeneous polynomials in n+1 variables, their zero locus is a typical example of such a gadget. And in this setup, the Hodge theory relates the topology of X, just stuff you get from X by thinking of it as topological space, with something that has to do with the complex structure on it. And so here's one way to formulate it. So I'll write it as an isomorphism. So you can look at the singular cohomology of X with complex coefficients. So this clearly just depends on X as a topological space. It's the first thing one learns about in an algebraic topology course.
You don't want to use that.
Yes. Thank you. Sorry, the question was I don't want to use the same n, and the answer is yes, I do not. Right, so you have singular cohomology, and then Theorem's theorem tells you that it's also the same as Theorem cohomology with complex coefficients. So this is the cohomology that you get by thinking about your favorite flavor of differential forms and looking at the closed forms modulo exact forms. So for example, you could do C infinity ones. You could also do holomorphic ones. You could also do algebraic ones. That still works. But the relevant consequence for my talk is what happens when you combine this with Hodge theory. And so then you get a decomposition. That looks like so. So the precise definition is not going to be relevant at all for what I say. Roughly, these are those cohomology classes which can be written in terms of differential forms, which involve I many dz's and j many dz bars in local coordinates. But the sort of big picture theorem here is that you have this kind of topological object which just depends on X as a topological space, and then it's identified with something that it clearly depends on the holomorphic function theory of X, because I talked about dz's and dz bars. And so, OK, this is great, but why is it actually useful? So it can be used in many different directions. I don't want to convince you that Hodge theory is useful in these lectures, but let me at least mention 2 examples of how one might use this that you can just see by staring at this theorem. So for the first one, let's try to understand how you can use this to go from topology to geometry. So let's say X is simply connected. That's a topological assumption on X. The fundamental group is 0. In this case, the first singular cohomology of X will also be 0 by algebraic topology. So H1 of X with coefficients in C is 0. And so therefore, the summands corresponding to 1, 0, and 0, 1 on the right-hand side both have to be 0. In particular, if you think about what it says for 1, 0, it's saying that there are no global differential forms which are of type 1, 0. So 1, 0 means it's locally defined just in terms of dz's. There are no dz bars. So it's actually holomorphic. And so what this theorem is really saying in that case is there are no global holomorphic 1 forms on X. So if you try to write down a holomorphic 1 form on X, at some point you're going to have to produce a denominator somewhere. There'll be a pole. It will not be defined everywhere. And so that's a geometric consequence about the sort of complex function theory of X that you're getting from the topology of X through this theorem. And you can also work backwards. And maybe I should have started there because it's easier. So if you look at Hn for n odd on the left-hand side, then the summands that show up over here for I plus j equals n, they come in pairs. I can swap I and j, and I get a different summand. And I comma j can never equal j comma I if I plus j is an odd number. And so what that tells you is that on the right-hand side, the vector spaces that show up, they show up in pairs. So the dimension of the right-hand side is even. And so therefore, you conclude that the odd dimensional cohomology of X is also an even has even dimension. And that's a highly non-trivial constraint. There's no reason a priori that a topological space would have odd cohomology, which is even dimensional. And you can use this to rule out to show that certain x's can never admit such a structure just by computing the odd cohomology and seeing that it's not even dimensional. So again, the specifics don't matter. What I'm trying to convince you is that this process of going between the topology of X and something related to the geometry of X can be used in both directions. And that's kind of the starting point of Hodge theory. And the starting point of these lectures is a defect of this theorem. And so the defect, well, there are various ways to say it, but maybe the first thing that might jump out at you is if you're interested in the topology of X, singular cohomology with C coefficient captures a lot, but it throws out some information. It throws out any torsion information. Like cohomology is really defined with integer coefficients. And then you just extended scalars to C to get the left-hand side over here. But when you do that process, you kill all the torsion information. And so you might wonder if there's some more differential / complex geometric way of capturing this torsion information. And basically, I'm going to try and give some kind of an answer to that. So the question that I want to formulate is how to understand the torsion cohomology of X geometrically. And I'm going to simplify life a little bit by focusing attention on p torsion, where p is a fixed prime number. So I guess I should have said this at the very start of the talk. Fix a prime p for all 3 days. And so if you're trying to understand a torsion abelian group, it breaks up into a direct sum of its p primary components. So you might as well focus the attention on those p primary guys. And that information is more or less captured by what this cohomology over here is. And so let's just try to understand this. So how to understand this geometrically, meaning in terms of function theory. And OK, this is you can certainly formulate this question. You might wonder why you care about this. Probably people have their own reasons to care about something like this. For me personally, and also I think motivation for a lot of the subject, comes from the fact that this is something of immense importance in number theory. And so let me just emphasize this. So y if X is an algebraic variety, so meaning, let's say it's in CPN, is defined over Q. So being inside CPN means that it's the zero locus of a bunch of homogeneous polynomials. And being defined over Q means that those polynomials have Q coefficients. So you don't have a pi in the coefficients somewhere. You just have integers. Then this theory of italic homology, pioneered by Grothendieck and Arden and a lot of other people, will tell you that this vector space over here actually has a very interesting action of the Galois group of Q. So the absolute Galois group of Q bar over Q acts on this cohomology, and it's one of the sort of most interesting examples of what's called the Galois representation, or most interesting sources of examples of Galois representations. So if in number theory we care a lot about trying to understand representations of this group, and these are some of the most important examples. So if you have a tool to understand these representations in some other way, you can imagine it would be useful in this endeavor. So that's maybe one reason you might care about this. And OK, so that's the question. And then the answer, which I'll try to convince you of in the rest of the talk, or the rest of the series, or at least a proposed answer. It's not a complete answer. But roughly, we're still going to do it geometrically. So we're still going to do it in terms of functions and differential forms and so on. But you can't do it on X itself, because X is a complex manifold. Functions are a complex vector space. You're not going to be able to detect some p-torsion information in terms of a complex vector space. Rather, you need to be in a setting where the functions themselves are a p-torsion object. And so what you want to do is you want to reduce X mod p. So let me write this. So this is the answer for X algebraic. I don't know what to do if X is not algebraic. But in the algebraic context, the answer that we'll try to explain is the following. So in the geometry of X mod p. Okay. And I'll make more precise sense of what this phrase means. But maybe intuitively, you can imagine that X is defined by some polynomials, and I want to reduce those polynomials mod p. OK, so that's kind of the goal. And what I'll do today is tell you one more precise form of this answer, and then some applications that answer has, which maybe a priori don't actually have anything to do with singular cohomology. Great. Are there any questions so far? OK. So let's be slightly more precise. So in my notes, I call this mod p Hodge theory. So let me write that over here. So the fact that it's mod p instead of p-adic corresponds to the fact that it's z mod p over here instead of some more complicated object. And so if you want to formulate a nice answer to this question, you need to be in a setting where you can get rid of the scare quotes over here. So you need to be in a setting where it makes sense to reduce mod p. But at the same time, you don't want to lose the ability to talk about, like singular cohomology with z mod p coefficients. So you want some, at the end of the day, you want to study some complex manifold. But you also want to be able to reduce it mod p, and there's a standard mechanism for doing this. And so here's, which is provided by the p-adic numbers. And so let me just very briefly introduce the setup. So Zp is a notation for the ring of p-adic integers. If you're not familiar with it, there's no problem. You can just pretend that it's Z localized at p. So you take the integers and invert all the prime numbers which are other than p. And you get some subring of the rational numbers. And for all intents and purposes for these lectures, there's not going to be much of a difference between them. So that's the object. The important feature of this object is that it has two interesting maps. So I can take ZP, I can invert P, and if I invert P, well, in this ring, if you invert P, you already inverted everything else. And so now if you also invert P, you just get Q. And over here, you get something larger, which is called QP, the ring of p-adic integers. But you can also go mod P, because I have not inverted P. So I can set P equal to 0. And then what you get is the finite field Fp with P elements. And so this is a field of characteristic 0. This is a field of characteristic P. And so somehow if you have some object whose coefficients are in ZP, then you can produce an object whose coefficients are in a characteristic 0 field, and also an object whose coefficients are in a characteristic P field. So it interpolates between characteristics, and that's sort of the role it plays for us. And if you want the complex numbers in the picture, you need to enlarge this slightly. So let's go to its algebraic closure. And let's also complete it. So I'm ignoring the fact that ZP had a topology, but if you remember that topology, then you have to complete the algebraic closure to get a field which is both complete and algebraically closed. And this field is actually isomorphic to the complex numbers. So non-canonically, yeah? If you believe in the axiom of choice, then this field is isomorphic to the usual complex numbers. And so to a first approximation, you can just pretend that this is the complex numbers. Let me call it C. It's the p-adic analog of the complex numbers. So this is the base I want to work over. And my geometric object, the X I'm talking about, earlier it was just a complex manifold, so it was somehow living over C. But now I want it to live over here so that I can also reduce it mod P. And so the precise words to say are X over ZP is smooth and projective. So you can, what that means is that it's cut out inside projective space by homogeneous polynomials. That's the projectivity part. And then the smoothness part is the same condition that you would have encountered in complex geometry. Certain Jacobian matrices have to be invertible to guarantee smoothness. But the important thing is that the coefficients are in ZP over here. And so there are two things. There are two more concrete objects you can get out of this. So you can get XC, which is a smooth projective variety in the usual sense over the complex numbers. So the kind of thing we cared about in these boards. But you can also get its characteristic P partner, which is XFP, which is now living in the world of algebraic geometry in positive characteristic. But so the picture that number theorists like to draw is you can think of ZP as a line. And basically, this line has only 2 points. And your X is some kind of a fibration over this line. So this is the point corresponding to FP. This is the point corresponding to C. And then the two fibers are these two objects I wrote down here. XFP and XS sub C. And the map really sort of looks like a fibration in that there's no sort of singularities in the fibers. Is that okay? If there are any questions about the setup, please feel free to ask. Okay, so now we are in a setting where we can at least try to make sense of an answer to this question. So I want to understand the singular cohomology with Z mod P coefficients, meaning I want to understand the singular cohomology of this guy over here, XC, with Z mod P coefficients. And the answer is going to be in terms of some kind of function theory on this object. So it will be Theorem theory on that object. And so here's one version of the answer that's precise. I guess this is so this is an answer from 2016. And it's not quite as clean as this thing over here. Like, it's not going to say that two vector spaces are isomorphic to each other. But there's a reason for that, so I'll get into it in a moment. So let's take A to be this ring over here. So formal power series in one variable called U over the field Fp. And so this is a p-ID. It's in fact a really nice p-ID. It only has one non-zero prime ideal. And then the theorem says that there exists a cohomology theory, which is called prismatic cohomology, attached to X, which takes values in finitely generated A modules. So instead of taking values in vector spaces, it's taking values in some modules over this ring. And it's related to the two theories that I mentioned before. So satisfying two properties. The first is if you take this theory and you invert the unique prime element U in this ring, you get the theory that you actually are trying to understand. So singular cohomology of Xc with Z mod P coefficients, except that doesn't literally make sense because this is living over Laurent series and this is just living over Fp, but I can just do the stupid thing and extend scalars. So it just looks like a copy of the cohomology we're trying to understand, thought of as living over some much larger ring.
So this C is the p-adic C or complex?
So the question was, what C is this? And it's the p-adic C, but it's also isomorphic to the complex C. So if you want to be strictly
So when you write XC, this is just the same topological space?
correct. So you can think of this as singular cohomology of a complex manifold you get from X if you identify the C with the complex numbers. More intrinsically, it's the étale cohomology of the scheme.
Then you don't need to use the topology of C.
Then you don't need to use the topology of C, which makes some people happy, right? And then something interesting happens when you sort of go to the opposite extreme. So instead of inverting U, you can try to set U equal to 0. So you mod out by U. And then what you get is roughly the de Rham cohomology of the Kersig P variety, XFP. More precisely, you get an injective map, and then the co-kernel of the map is related to the U torsion on one higher degree on the left-hand side. It's a universal coefficient type relationship between this theory reduced mod U and this guy. And maybe I should say something about what this is. So one of the advantages of doing de Rham cohomology purely algebraically, meaning you just work with algebraic functions and algebraic one forms and so on, is that you can do it in any setting. You can do it in Kersig P. You don't need some notion of analyticity or holomorphy to talk about it. You can just, if I give you equations for the variety, you can write down the de Rham complex and compute this cohomology. So this is a very computable object attached to X. And if you were over the complex numbers, it agrees with the usual de Rham cohomology. Thank you. Yes, the question was whether I mean X or A. Absolutely, I mean X. Okay. And so, I mean, I don't know, if you like pictures, the rough picture is that you have like the U line over here over Fp, and then you have a family of cohomology theories that's parameterized by the U line. So at U equals 0, you have something sticking up, which is de Rham cohomology of XFP. And then the general value away from U equals 0 is this étale cohomology. And the picture is supposed to be suggestive in the sense that what's happening at the special point is going to be bigger usually than what's happening at the non-special points. Like if you think about a family of matrices and you look at their co-kernels, the rank can go up at certain special values. And that's the kind of phenomenon that's taking place over here. Okay, great. Are there any questions so far? I'm going to write down a corollary of this in a moment. But I'm happy to answer a question if I'll raise the board.
So is this isomorphism A or is this isomorphism?
Good question. So the question was, how canonical is this isomorphism? And the answer is that it's not at all canonical. I was cheating. The way to make it canonical is to enlarge this to a certain period ring.
So it recovers the usual comparison.
Yes, right. And so an immediate corollary of just having this picture is a purely numerical one. So let me just emphasize that. So I can look at the FP dimension of the thing I care about. So the singular cohomology with mod p coefficients. And as the picture suggests, it can only go up under specialization. So the value at the special point is going to be bigger than or equal to value. So you get this numerical inequality, and I left space because I wanted to just remind people that there's a similar inequality that's much easier, just coming from the universal coefficients theorem in topology, which is if you look at the dimension of the singular cohomology of X with Q coefficients over Q. So this one is just kind of formal, and this is the theorem. But this is the sense in which I'm saying that this is some form of mod p Hodge theory. It's telling you that if you see a non-trivial cohomology class with mod p coefficients, you should also be seeing a differential form somewhere else, witnessing that cohomology class. It's just the differential form doesn't live on your original X. Rather, it's living on some characteristic p partner of X.
If you don't have a good reduction modulo P, can you prove inequality of this form?
OK, right. So the question was, what happens if you do not assume good reduction mod p? So one answer is that I don't know what to put on the right-hand side, because the Rom cohomology of singular varieties in characteristic p is pathological. The standard setup in which this comes up is if you have semi-stable reduction. So it's not quite a good model, but the central fiber could look like that. And in that case, there is a semi-stable version of this entire picture. It was developed by Chisnavikus and Koshikawa. Yeah, thanks for the question.
But in general, it's not like
Correct. In general, I do not know a good way to sort of, like a good candidate for the right-hand side. Right. So actually, let me make some remarks on this related to that. So first one, I guess I already mentioned that there's a semi-stable analog. Maybe the easier thing I should have said is that this inequality, let me call this inequality star. So this star can definitely be strict. I mean, both of them, but the second one in particular can be strict. So the relationship is not going to be as nice as in classical Hodge theory, where two sides are isomorphic, because they just have different dimensions. So they cannot be isomorphic.
is the composition of these inequalities elementary?
The composition, yes. Because you can, sorry, the question was, is the composition of the inequalities elementary? And the answer is yes. Because instead, in the middle, I can just put Rom cohomology of X sub C. Yeah. And the second remark, which is mostly related to my talk tomorrow, is that this theory has, so this is theory is an example of what's called prismatic homology. Example because there's some sort of freedom over here in choosing your A, and there's some art to it. And so it's an example of prismatic homology, and one of the sort of defining features, which is not at all apparent from what I've told you, is that this has a natural Frobenius action. So there's an operator acting on it, a linear operator, which really helps you sort of understand the structure better. And this operator will show up more tomorrow, so I just wanted to mention it right now. It has to do with the fact that there is this kind of extra arithmetic parameter u, and that needs to be accounted for somehow. can you refine the inequality using the Frobenius action? I'm not sure about that. What the Frobenius action lets you do is that it lets you pick out this summand from the tensor product. So you can genuinely isolate a homology, not just this enlarged version of it.
So this doesn't mean that this thing is a subportion of the set.
Sorry, there are too many thises in that sense. This doesn't mean that.
So what Roman was asking is, so let's view them as modules over the polynomials of Frobenius.
Uh-huh.
So then the thing in the middle, subportion of the thing.
Ah, okay. So the question was, if you keep track of the Frobenius, is it true that the thing in the middle is a subquotient of the thing on the right? And that's a very good question, and the answer is almost surely no. So more precisely, there's a mod p squared version of this rather than a mod p version of this. And then in the mod p squared version, there are examples where the left-hand side is a z mod 4, and the right-hand side is z mod 2 cross z mod 2. So one's not a subquotient of the other, even though they have the same length.
See, that might be a bit like a spectral sequence that one is associated ring, but one is a subportion.
Well, sorry. I don't know how z mod 4 can be a subquotient of z mod 2 cross z mod 2.
No, but maybe the thing in the middle has a configuration such that it's associated ring that is.
I don't think that's true, but I don't have an example off the top of my head. Yeah. Right. Okay, so I wanted to mention, okay, I want to spend most of the remaining talk talking about applications of this, which will in some sense be much lighter than what came before. But let me at least mention first some sort of a short history of the constructions. Of this theory. There are actually multiple constructions by now, and they've each sort of shed light on a different part of the subject. And so the first one was an analytic one. More precisely, p-adic analytic. It uses perfectoid spaces. And it's probably it's the easiest one to write down if you just want a formula, but let me not do that. The second one is a homotopical one. So there is a construction of this Chromology theory that comes from algebraic topology, more precisely through this machinery of topological Hodge homology. And that's very useful in both directions. So in proving stuff in algebra from topology and also proving stuff in topology from algebra. And so I'll spend more time on this on Friday. And then there's sort of a purely algebraic one, which came maybe 3 or 4 years ago now, which is where the name Prismatic Homology comes from. This is where the notion of a prism was finally coined. And this is, in some sense, the most flexible. So if you want to do computations, this gives you more explicit models, local models for what's going on compared to the previous two. And then in the algebraic side also there was like, okay, maybe I'm going into too much detail, but let me write this. So there was the original side theoretic one, which I will not talk about. This was, oh, sorry, I've been careless about attributions. Both of these were those authors over there. This one was myself and Scholze. And then there's a more recent one, which in my opinion is the most useful one, which is using the language of algebraic stacks. And so this was in joint work of myself and Jacob Lurie. It started the last time I was at MIT. And then also Drinfeld discovered a lot of the same ideas independently. And I will try to come back to this later in the lectures. But there are these 3 approaches, basically, to trying to define these invariants. And none of them is like super elementary. So it would be nice if there was just something very simple that you can just write down. But each one of them requires some non-trivial input. OK. So my plan in the rest of the talk is to just mention a few different applications of this theorem. The applications are not like immediate, so I'm not saying that you just take the theorem and then spend like 20 minutes thinking about it and you get the application. These are all non-trivial theorems. But I just want to explain the kind of questions you can try to answer by using this tool. So some recent uses of this theory. And so the first one just comes from this observation on top. So I have this corollary, which is this kind of sequence of inequalities. And it's very easy to see that, OK, let me just write. So you get the corollary gives you a torsion freeness criterion for chromology. So it gives you a criterion for detecting the lack of p-torsion. And more precisely, what the criterion says is that if the dimension of the de Rham cohomology in Kirsig 0 of your xc is the same as the dimension of the de Rham cohomology in Kirsig p, so this is over c and this is over fp, meaning that the leftmost number and the rightmost number are the same, then there is no p-torsion in the cohomology in that degree. I mean, roughly, if you have p-torsion, then the p-torsion will contribute to a non-trivial element of mod p cohomology, and therefore the dimensions will be off. So actually, as I say that, it strikes me that I'm off by 1 somewhere. OK, it's plus or minus 1. I'm not going to be able to chase it at the board. And so this is a checkable criterion. It's telling you that if you want to rule out p-torsion in singular cohomology, one way to do it is to compute this guy, which is just usual singular cohomology with q coefficients by Kirsig 0 stuff. And this guy, which is defined purely algebraically in terms of the equations defining x. So if you have some control on what x looks like mod p, you could compute what this looks like and then hope for an accident. And so this actually happens. And so there's this really nice result by Colmez, Dospinescu, and Niziol, which used exactly this idea in a case of interest. And so what they checked is that the cohomology of what's called the Drinfeld upper half space is p-torsion free. So this is a space that's of interest in arithmetic geometry. It's a p-adic analog of the upper half plane, or a higher dimensional version thereof. And they were able to sort of understand the geometry of its mod p reduction explicitly enough to try and run this strategy to get torsion freeness of cohomology. So that's a pure Kirsig 0 consequence that you get out of this. No, they use the corollary to prove this. They use the corollary and apply to the standard semi-stable model of Drinfeld upper half space and then compute its mod p reduction. Yeah. I mean, they get much more than this. So this is the simplest thing I could state in this talk. But really, you care about these objects not just as modules, but as representations of certain groups that are acting. And they compute it as representations this way. The second theorem I wanted to mention was the following. So it's based on the idea that, I mean, essentially what this theorem is saying, that I just erased, I guess, that there's a way to go from mod p cohomology classes that you care about to differential forms somewhere else. And with differential forms, you can often do local arguments, right? So for example, if you have a globally defined differential form on a variety, so a holomorphic form, there's some analytic continuation principle. It cannot vanish on an open subset. If it vanishes on an open subset, it has to be 0. That kind of statement is not true for cohomology classes in general, but only for global forms. And so that's useful because sometimes you can get lucky. And so here's one application of how they do this. So you may sometimes view a differential form alpha, or sorry, a cohomology class alpha as a globally defined differential form. On X mod P. And then you can make local arguments. And so an instance of this principle in action was a recent theorem. So this was from last year, I guess, of Farb, Kissin, and Wolfson. It's a theorem in algebraic geometry over the complex numbers. And what they prove is the following. So you take a complex abelian variety, so a complex torus which has an algebraic structure. You pick a prime which is big enough. They're more careful about what big enough means, but I think the theorem is already interesting for sufficiently large P. So for P sufficiently large, what they were interested in was trying to understand the number of parameters that are needed to define finite covering spaces of A attached to multiplication by P. So for P bigger than or equal to 0, the map multiplication by P from A to A. So this is a covering space, a finite covering space whose Galois group is the set of P torsion points on this complex torus. And they were interested in trying to understand the following question. Like, can this map be actually defined over something much smaller dimensional? Like, is there a curve that A maps to and a finite covering space of the curve such that this map is pulled back from the covering space of the curve? And the answer is no, it's never possible. So the map P is not pulled back even birationally, so even on a small enough open subset from a smaller dimensional base. So if you're thinking in terms of function fields, so an algebraic variety has a function field. And what this is saying is that to define this finite degree P to the whatever cover extension of the function field of A, you really need to be working over a field of transcendence degree, at least the dimension of A. It cannot be defined over something smaller. So it's a result in pure geometry. But as far as I can tell, the proof goes through all this stuff.
P does not need to be defined over any number field.
Correct. Yeah, A can be anything, yeah. Sorry, I wasn't repeating the questions. The question was, is this true for non-algebraic abelian varieties? The answer is I don't know. I'm not sure. I mean, right. I think their proof would work for p-adic analytic analogs of complex tori, but I don't know if they would actually work for complex tori. Right, great. Okay, so that's another application also in algebraic geometry. I'm an algebraic geometer, as was said earlier, so that's where most of what I write will come from. So the third one is mostly what I'm going to talk about next time, so tomorrow. So you may use this Frobenius action on this Chromology theory to prove vanishing theorems in Kersig P. To prove vanishing theorems over the p-adic numbers. And so what I mean over here is that there's a famous vanishing theorem in complex geometry called the Kodaira vanishing theorem. And there's an analog of that. One can prove in this setting using p-adic Hodge theory. And this has sort of more tangible applications. And so this has applications to the minimal model program in small dimensions over the integers. And so this is all, I mean, this is mostly the subject of tomorrow's talk. So it's in the birational geometry direction. So maybe that was not such a useful thing to say because I didn't actually say anything concrete there. I apologize. But here I will say something concrete. So, so far I talked about everything having to do with algebra. But I mentioned over here that there is a homotopical construction of prismatic homology. But if you instead use the algebraic construction, then this approach gives you a new tool in homotopy theory, because it says that there's a way to compute certain invariants of interest in homotopy theory using certain objects coming from algebra. And so you can actually use this. So it leads to new calculations in algebraic K-theory. And I'll just mention one. So this is super recent. It's actually from 2 weeks ago. It was on the archive. There's this really nice announcement by Anteo, Krause, and Nicholas, where they make substantial progress on what I believe was a big open question in K-theory. So let me just write it this way. So pi 2I of the algebraic K-theory of z mod p to the n is 0 for I sufficiently large. So in algebraic K-theory, computing the algebraic K-theory of rings like this was a prominent open question. You could, for n equals 1, so for z mod p, this was Quillen's calculation of the algebraic K-theory of a finite field. But for n bigger than 1, we basically were stuck for a long time. And what Anteo, Krause, and Nicholas observed is that this homotopical approach to algebraic K-theory combined with some new observations they made about that approach give you a tool for, or an algorithm for computing all of these groups. And then if you stare at the algorithm carefully enough, you get this vanishing theorem as a consequence. But I believe they actually get like a fuller description. Like I think you can program it into a computer to compute the rest of them. And the bounds are also precise. You don't have to say sufficiently large.
Is this bound dependent on n?
Yes. The question was, does the bound depend on n? Yeah, absolutely it does.
It actually depends on n for only the proof bound.
I believe it actually depends on n. In the sense that, so there's a version of this theorem not just for z mod p to the n, but also ramified rings of integers reduce mod p to the n. And if the bound was independent of n in all those cases, you'd get a contradiction with the known theorem in the direct limit. So I'm pretty sure the bound depends on n. Okay, and then finally I wanted to mention one more application, which was to some new structures on Theorem Chromology. And so this, I guess I erased this, but I mentioned that there was this stacky approach to prismatic homology. And it really seems to shed some light on some arithmetic structures on various cohomology theories that we hadn't sort of seen before. And here's one, I think the most tangible such result, so I guess. I mean, it's part of this package. And so if you have this x over zp as before, so something smooth and projective, you can look at the Theorem cohomology of x reduced mod p, as I have been doing. And what this approach tells you is the fact that the mod p guy was actually the mod p reduction of something defined over zp means that it carries some extra structure. And you can name what that extra structure is exactly. And so it's the following. So there exists a natural operator theta. We call it the Zen Operator, acting on the Theorem homology of the mod p guy. And it's non-trivial. So one way to say it's non-trivial is that it interacts in a specific way with the conjugate filtration. So if you don't know what this is, please just ignore it. But in characteristic P, Theorem homology carries a natural filtration called the conjugate filtration. The operator preserves it, and it acts on the ith graded piece by minus I. In particular, what this tells you is that if you're in characteristic P and you only have sort of graded pieces corresponding to integers which are smaller than P, then all the eigenvalues that show up mod P are distinct. And so if you can just take the eigenspace decomposition, and they'll tell you the conjugate filtration splits. And so one concrete application is, and this is the last thing I'm going to write, so I can write it over here. You recover the Deligne-Luzzi theorem on the degeneration of the Hodge Theorem spectral sequences in characteristic P. So Deligne and Luzzi gave the first algebraic proof of the degeneration of the Hodge Theorem spectral sequence. And this eigenspace decomposition recovers that theorem and, in fact, gives you more information in higher degrees. And so I think it's a question of interest to try to understand sort of the residual nilpotent operators you would get from this operator once you sort of account for the fact that you have this degeneration. Okay. I think I've more or less set up what I wanted to say. So let me stop here.
Any questions? Is there some specific small dimensional example of X for which this inequality is
Specific small dimension examples of X where this inequality gives something new. Okay, so I'm not sure if this counts as something new, but maybe it's an explanation of something. It's a new explanation of something old. So you can look at Enrique surfaces in characteristic 2, or when P equals 2. And it was known classically, so if you work mod 2, they fall into 3 types, corresponding to Z mod 2, mu 2, and alpha 2. The 3 group schemes of order 2. And it was known classically that in all 3 cases, the Hodge Theorem spectral sequence does not degenerate. So it was known classically that the Theorem homology is bigger than what you would expect from characteristic 0. But the proof was computational. So you go through the Bombieri-Mumford classification and just compute in each case that the dimension is bigger than what you would expect. And what this inequality will tell you is that that had to be the case, because in characteristic 0, there's 2 torsion in singular homology. And so that's one way in which you can use this, which is as soon as you see P torsion in characteristic 0, you expect the mod P homology to be bigger than what you would naively expect.
Okay, right. So if I'm correct, there is some application of this sort of ideas, but I don't know if it's actually this related to computing homology of classifying spaces of equal, form of equal.
Right.
Can you say more about that?
Okay, so Roman's asking about what happens if X is the classifying space of a compact Lie group rather than an algebraic variety. And I think, well, I mean, you should know this better than me, because your student wrote a thesis on this, and I believe he proved it. Yeah, so I think Kubarak and Prikodko, they proved this inequality for BG, for a G a reductive group. Sorry.
So in order to have this operator, do we need X to be over ZP, or is it enough to have it over Z mod P to the N for large N?
It's enough to have it over Z mod P squared.
And what if you can lift further over Z mod P cubed, do you get something shorter?
Yeah, so the question is what happens if x is not over zp, but just over some z mod p to the n? So the first observation was that already if it's over z mod p squared, you will get this structure. And then the second question was what happens if you know that you lift further? Do you see some additional structure? And
Anytime you can lift to the next level.
you do, but I don't know how to write something concrete about it. So you basically, if you lift to level n, but you'll see an action of something that looks like a divided power algebra. And if you lift to level n plus 1, you'll also see an action of something that looks like a divided power algebra. But the map between the divided power algebras as n varies is the 0 map. So something funny happens. Yep. So the question was, is the cohomology theory and the theorem of a cohomology theory? Okay, so again, I'm probably going to butcher the answer. My impression was that a wave cohomology theory needed to have coefficients in a field of characteristic 0, or at least in a field.
Yeah.
So, I mean, then this would not work because it's the coefficient ring is a DVR, not a field.
Does it have like some kind of concurrentiality?
Yeah, so you have to do everything. Everything is slightly funny because it's over a DVR instead of a field. But if you work in the derived sense, it has Poincare duality, and it has cup products, and it has a Kuhnert formula.
And it has some kind of cycloclass map?
It has a cycloclass map, and yeah.
So if you have a variety over FP, then its lift over z mod p squared are described by some homology, which describes deformation. Is that linear with respect to this homology?
I haven't thought about it. So the question was, if you think of theta as a function of the lift of x to z mod p squared, what kind of linearity properties does it have in terms of the lift?
It's in a torsor.
Right, the set of all lifts is a torsor for a certain vector space.
And what kind of function is theta on that applied space?
Okay, I didn't think about it, so let me not give an answer. But yeah, thanks.
But it could be interesting, yes?
It could be interesting, and I suspect I think the question is answerable, just not by me standing here right now.
Can you say one word about where this thing comes from?
Okay, so I can, let's see, can I? Okay, so I can tell you kind of the bullshit explanation and then a mathematical one. So the BS one is that in this prismatic approach, you're kind of trying to, okay, I don't know how to make any of this precise, so I don't think this is just some picture. You want to think of Z as a curve over something else. And in that picture, this theta is something like a Higgs field. So it's like the Higgs field of Z relative to the base. Now, you can't quite make that precise, but the way it precisely comes about is that, so for any x, which is a p-adic formal scheme, this stacky approach to prismatic homology produces a stack, which is called W card of x. And then whenever you have some y over x, its relative homology is really a quasi-coherent sheaf on the stack. And then the way this theorem is proven is by understanding the stack when x equals z mod p squared. And it basically looks like if x is z mod p squared, the stack looks like a B GM sharp. So you take the divided power hull of the origin inside the multiplicative group.
You mean spec or?
Yes, I need spec. And so representations of this group scheme are the same as operators like over here, whose generalized eigenvalues are all integers, like over here. And so that's where it really comes from.